For as long as Nintendo has been making video games, they've been building in copy protection and region locking. And as long as there's been copy protection, there have been people breaking it. Today, Pluto, Derek, and Nervert return to enlighten us on the state of the Nintendo Switch. Give them a round of applause.
Hey guys. Oh. Is it working? Oh yeah, cool. Okay. Hey, I'm Pluto. This is Derek and Nervert. And yeah, first off, we try to be ethical hackers, so we don't really condone piracy, and we really just want to do creative things with hardware that we own. So yeah, and so the Nintendo Switch was released about 9 months ago, and we've been playing around with it since. It's been really successful. Like, it sold a lot of units, and so, but we want to hack it, right? So the usual entry point that you do is you go via the web browser, and the Switch has a web browser, but it doesn't have a generic web browser. So we found a way to launch the browser, but it's not actually intended to be launched this way. So there's this Tetris game that you can buy. Yeah, it will take some time. So you go into the main menu, you press the right trigger button on your right Joy-Con, and it launches the game manual. And then you go to the menu, and you go all the way down to the bottom. And then they included a link to their website. Takes some time, spraying the heap and stuff. So. Oh, wait. I hope I didn't break it. Oh, sorry, I broke it. Okay, so one more time. So this was actually the WebKit exploit that we use. It's a really old one. Like, it was 6 months old at the time that the Switch was released. And we didn't even have to find our own. We could just take a public one and yeah, use that. So. It's pretty painful doing this over and over, but I've gotten used to it. Like, I've done this 1,000 times. It's the Wi-Fi. Yeah, I don't have one, sorry. Oh. Oh, this was not the way we intended it to be, but maybe we can try it later. So sorry. Um, maybe you can go into the menu, yeah, later. Okay, so we're talking switch security. We'll get the demo working for later. So, okay. So the switch is actually quite a powerful unit. It's a hybrid handheld and stationary console. So it has a quad core that's clocked at 1 gigahertz. It's an A57 ARM. And it has an NVIDIA GPU Maxwell architecture. It's clocked on either 384 or double that, if depending on if you're docked to a power supply or not. So if you're running off battery, they want to reduce the power consumption. It has plenty of memory, like 4 gigabytes of DRAM. And then there's the selling point, pretty much. It's the Joy-Cons, and those are detachable. So you can either play yourself, or you can share one of the Joy-Cons with a friend, and you can play 2 players. They have all the nice sensors, accelerometer, gyro, NFC, IR. And they have this feature called HG Rumble, but it's just a vibrator. And these ones don't have any security at all, so you can just unscrew them, look at the part number, Google the part number, get all the data sheets, and dump the flash. It's all plain text. But when you open the main unit, this is what you see. You have the 2 DRAMs, it's in the orange section. And then you have the main CPU, which is in red. And then the rest is just power management, Wi-Fi, boring stuff. So, oh yeah, and the flash, they actually made a separate daughter board for the flash. So we can easily just unplug it and dump it and stuff. And yeah, the code name for the switch is hack. I'm not sure what they were thinking, but yeah. When we look at the main CPU, it's branded ODN-X02. It's like, because Nintendo is the ODM, this chip is actually just got from NVIDIA. And NX is the code name of the Nintendo Switch. But it turns out that the part number is just a lie. It's just a regular Tegra X1 NVIDIA chip. Like, people decapped it, and it looks just the same. And yeah, we have the reference manual online. It's freely available, pretty much. It's 3,000 pages. So it goes into detail, pretty much everything except the security part. But they also provide their own Linux drivers that, yeah, we can get the security, at least some of the security registers and everything like that. The main overview of the SoC is that you have an ARM7 boot CPU. It does power management, and it has a boot ROM. It also has some internal SRAM. And then you have the main CPU, and it has 64K of SRAM. That's for trust zone, so it's secure bus, secure access only. And then you have the GPU on the same die. And then you have the security engine that does RSA, EAS, acceleration. It can DMA and stuff. And then they have on-die fuses, a lot of them actually, like 1,000. And then they have the memory controller. They have a TSEC, which is security CPU. It's a really weird architecture. They were really creative. And then they have the DSP, which is kind of boring. And then they have a bunch of buses that you can talk to external devices. So the highlights for the fuses, they use it for a lot of stuff, configuration stuff, but they have 32 bits dedicated to downgrade protection. So every time they have a vulnerable firmware, they can just burn a fuse. And every bootloader reads the fuse to make sure that the number of bits it expects is actually set. So if you try to downgrade, just rewrite the flash memory, it will not boot because there's a fuse inside of the CPU that says, oh, we're not allowed to boot this anymore. So, and then they have the SPK, which is a just normal AES-128 AS key. And it's the source of all the confidentiality in the system. So this is what you want to have if you want to decrypt all the software. And it's also in the fuses. And you can disable this one later on in boot, so you can only access it during early boot time. And then they store the hash of the RSA public key, which is how they verify the firmware binaries. But they don't store the actual key, they just store the hash because they want to save space, but it's equally good. And then they have this cool feature that they can patch the boot ROM, so they can store patch instructions for how to modify the boot ROM code. So if they have exploitable bugs in the boot ROM, and they do, they can actually fix them, which is, they can fix it at factory time. So they actually filled up all of this space just fixing bugs. And it turns out that since this is just an off-the-shelf chip from Nintendo, from NVIDIA, sorry, they actually just provide this dev board you can buy from them. It's $700, or half that if you're a student. So this gives you access to, you can play with all the I/O and discover what's undocumented about it. And if we look at the software, so there, there was this rumor it was running FreeBSD, and everyone was asking, does it run? No, it doesn't run it, and stop asking. Instead, it runs a custom microkernel called Horizon that's been in development at Nintendo for the 3DS. So it's yeah, like 8-9 years old maybe. All the drivers are running in user space, and they're called services. So it's a microservices architecture. And then they have a custom NVIDIA graphics driver that's kind of similar to the Linux driver, but they modified it a lot. And then they have a custom API to talk to it. So they have it kind of is like Vulkan, like it's a really thin abstraction on top of the GPU. And it's custom, it's undocumented for us. So if you come from the 3DS hacking scene, we can do a comparison. So the main difference is that all userland processes now have ASLR. So all the drivers and all the games are using ASLR. So since it's randomizing the address space, and that makes it really hard to exploit save games, because if you just have a file format bug, you really can't do much if you don't know where things are in memory. And they rewrote everything pretty much, just refactored, and renamed everything. But if you just switch out the abbreviations, all the concepts are the same. They don't have a security processor like the 3DS had ARM9. It was a big problem in the 3DS because it was a, oh, sorry. Shit. Let's see, go back. So 3DS had this ARM9 processor, which did a lot of stuff. It was a big attack surface, and it didn't have any memory protection. So they removed this. Now everything is running on the same CPU with memory protection proper. Yeah. So the security model they have is the most privileged part is trust zone, and it just is a crypto interface pretty much. It's designed in a way that the keys never leave the trust zone. Hopefully, well, that's how they wanted it. So it kind of works like a hardware secret. And then you have the kernel. So its goal is just to enforce process isolation and communication between processes. And it also has the IOMMU. It controls the IOMMU. And then it has what we call base services. These are processes with ASLR and everything. And there's the FS module, which is the file system driver. And NCM, which is not really interesting. And SM, which is a service manager. This one is pretty interesting. It enforces the whitelist of which process is allowed to talk to which process. And then there's PM loader, which just loads and creates new processes. And then SBL, which is the interface to trust zone. And then they have a bunch of microservices like the GPU driver, Wi-Fi driver, Bluetooth, yeah, stuff like that. And then finally, we have, at the lowest privilege level, we have the game or the web browser. So the web browser game sandbox, we only get access to approximately half of the syscalls. And there are 40 user services, which are services that you're supposed to access as a user. And it has a concept of per process file systems. So a game can really only access its own save data and save games. And it can't mount SD card, which is, when we want to make a homebrew exploit, for example, we want to load files off SD card like elves. But yeah, we can't do that just from the browser alone. And then the service sandbox, which is where all the drivers are at. We have like 20 more syscalls. It's mostly just for talking to DMA devices and handling IPC communication. It has a service whitelist, but it's vastly reduced, but you get access to a few more. And the services don't have any file access at all in general. There are a few exceptions, but this is pretty powerful because even if you were to elevate, let's say, go into the GPU driver, you don't get any extra file access as a result. And they sometimes need to talk to external devices, so they have MMIO mapped. But even if a malicious driver tries to do a DMA request outside its own process address space, the kernel is actually the one who maintains the IOMMU for all the bus masters. So a malicious driver cannot really ask the device to do something it's not supposed to do. The base service sandbox, which is those 5-6 processes that are special, they are bundled inside the kernel package together with the kernel. And they have approximately the same syscalls as normal services. But these ones don't have a service whitelist, because these ones are the ones that actually enforce the whitelist. So you can't, like they're the ones who enforce it and also fill it in and maintain it. So they can't check themselves, basically. And they also, because they maintain the file system, they have no whitelist for files. They can access everything, basically. So yeah, we're going places. And we start from the lower, like the most unprivileged part. And yeah, so we start with WebKit, as we're going to demo later. And yeah, so they've had a bunch of bugs here. They fixed them all, but it just keeps coming more. It's used for eShop, like when you buy games online and manual and other stuff. But it's also always over HTTP, or yeah, when we can't control the data, except with this one game. Also, firmware 2.0 implemented a new way of launching the browser. You can just create a new access point and act like a Wi-Fi. And yeah, you can just render arbitrary HTML because it thinks it's a login page for a protected Wi-Fi network. And yeah, we just took this Pegasus exploit and it just works. So when we dump the memory of the browser, the first thing we find is that it's dynamic linking with a file called SDK. And when we run strings on it, it's not an elf, but we converted it to an elf. We get pretty much all of their function names, which is really nice when you're reverse engineering stuff. We get names of all the syscalls and all the fancy some of the crypto stuff. Yeah. So yeah, this is what we're going to demo later. So the game application, yeah, they knew we were going to get this at some point, and with WebKit it's pretty easy. So what we did then is we're trying to black box, trying to elevate our privileges from the sandbox. So my handle is Pluto, and there's a service called Plu. So I don't believe in fate, but yeah, I looked into this service, and it's a user-accessible service. That's what the U is for. We think PL is for preload. There are 3 commands that take an integer, signed integer, and if you feed it a big value, you notice it crashes. And this is just like an array out-of-bounds read where we control the index completely. So we can just give it a negative index, and we can read out the entire binary of service. So this way we can dump the code of NS, which is one of the yeah. So we managed to get one of the microservices for just black box poking things. And now we're going to look into the SM, which is the service manager. It's the one that enforces the whitelist of which services you're allowed to access. So the way you ask it for, you give it a string, and it gives back a handle to that service that you asked for. And you send it a PID, you send it your PID, so that it knows which whitelist to enforce. But yeah, what if we just don't call the initialize function? So we never actually give it our PID. turns out that the variable that's supposed to store the PID is uninitialized. It will just be 0. So SM thinks we're a process with PID 0. Yeah. And then we get access to everything. So, but we can talk to everything, but we don't have the code. So what we want to do is we want to dump all the code in the system so we can analyze it. So if you look how the binaries are launched, it's launched this way. And all the code comes from this FSP loader service. It has a function called mount code. So we just need to connect to it and read out all the binaries, right? But when we try to connect, we get some error message. Turns out the kernel enforces you can only have one session at a time. But this session is currently held by the loader. So the loader has a session to the file system driver. But if we crash loader, the kernel will garbage collect, the reference count will go to 0, and it will release the session. So we found a command in loader that you just give it a thread handle, and it crashes. So we get all the code binaries, just can read them out. This is really nice as well. Now we can really understand the system a lot better. And finally, we're going to look at kernel. And for that, we're going to take a little bit of a detour. So Derek is going to talk next about what happens before the system has booted up. So.
Okay, it seems like we lost some time on the demo, so I'm trying to hurry a little bit. So far this was all achieved by just using black box testing. And you know, black box testing is fun, except that it's not, because, well, the switch uses a microkernel, and that means the attack surface is pretty low. It seems quite unlikely that you will get some read primitive where you can just dump the entire kernel. And also, there's ASLR in the privileged processes, so you might even need 2 vulnerabilities in the process to get access to, like, kernel system calls that only privileged process can use. So yeah, black box testing on the kernel was kind of a dead end for us. And when you think about the chain of trust, WebKit is pretty much at the end. So maybe it's a new console, so maybe why not just start at the other end? So we're gonna have a look at the boot sequence. And it's very cool because it's all documented publicly by NVIDIA. And yeah, you get a bunch of information just for free. And the way how it works is there's a boot ROM that runs on the ARM7, which is like a super old and crappy CPU that they call the BPMP, which means like boot and power management processor. And this is actually not a custom boot ROM. It's written by NVIDIA, but as Pluto already mentioned, Nintendo has some custom patches on it. The boot ROM will, well, as it is explained in the documentation, it will just load the BCT, which is the boot configuration table, and the second stage loader from eMMC. So at this point, you don't really need to know what the BCT is, but basically it tells the boot ROM where the next, where the second stage loader is located in the eMMC, and it also contains the signatures. So when that's the usual boot flow on the switch, it will try to boot from eMMC, but if that fails, because, for example, the eMMC is missing, it will enter a recovery mode, which allows you to send USB messages to the boot ROM. And if you might think, yeah, this is the ultimate backdoor, well, unfortunately, it's not, because all messages must be signed by using Nintendo's private RSA key, and of course, we don't have that. But what we can do is we can dump the eMMC, which is like super easy, and we did that. And we got a pretty nice overview of all the boot components that are stored on the eMMC. So this is a little bit complicated, but what you can see is the boot ROM on the left. It loads something that is called package 1, which is basically the second stage bootloader and next stage in one image. And the first part is actually stored on eMMC in plain text. It is not encrypted. And the other part is encrypted by using universal encryption keys. There's no console unique encryption there. So how does it work? How does the package 1 loader decrypt the next stage? So they have this feature where they load a key blob from eMMC, which is console unique, and it basically contains encrypted keys. And package 1 loader generates a key blob key to decrypt that key blob, and then it uses the decryption keys from that key blob to decrypt the next stages. So we would like to get this key because the kernel is also encrypted when it's part of package 2, as you can see on the right. And well, this key is only available to this package 1 loader. So that means we need to get code execution in package 1 loader. Okay, so how do we dump keys? Well, in the past, as you might know, we glitched the 3DS and got the keys, and we glitched the Wii U and got the keys. So maybe, maybe you can glitch the Switch and get the keys. So we wanted to try that, and in order to do this, you want to get code execution package 1 loader, and basically you want to glitch the component that loads the package 1 loader, which is the boot ROM. But how is this actually verified? So the boot ROM uses that BCT, which I've already mentioned. And this is basically a plain text blob stored on the eMMC. And it contains all the signatures of the bootloaders. And then there's a RSA PSS signature on top. RSA PSS is a really strong signature scheme. And it uses the RSA public key, which you can see on the top, to verify the signature. And this public key is hashed. And this hash is stored in the fuse of the device. So you cannot change it. Basically, what we want to do is, when the boot ROM verifies this public key using the hash, we want to glitch this hash check, because then we can put our own public key and our own BCT signatures, and with that, our own bootloader signatures, so we can sign our own bootloaders. Okay, but we don't. We didn't have the boot ROM then back there, and we didn't know when this check, like the hash check, when does it happen. So we have to find the timing for it. And for that, we can take a look at the eMMC bus. You can just sniff it. So we get a really nice dump of all the commands that are issued by the boot ROM to the eMMC. So you can see the diff. It's the time difference between each command that was issued. And it's basically the time that the boot ROM needed to do some operation between those reads. So when the BCT was good, it took quite some time to verify it. And when you put like an invalid public key in the BCT validation will fail, and it will actually start reading the next BCT. And then you can see the difference is much smaller. So that means the boot ROM will see, oh, the public key is wrong. I will not try to verify the rest of the BCT. And with that, they basically leak the time of check when the boot ROM checks the public key hash. Okay, so this was all in theory. Basically, it took like 1 month to develop a glitching setup, and this just uses power glitching. So what I did was I first desoldered all the capacitors on the voltage rail that powers the ARM7, and then I've used an FPGA to basically control some MOSFETs, and those MOSFETs will pretty much lower the voltage for a short time. So hopefully the public key hash check will fail. And then when you get code execution, we are pretty lazy and we just bit banged the eMMC clock because we actually found some clock divider register. So basically by changing the frequency, we could encode the data of all the secret keys bit by bit, sending it to our FPGA. And then we got all the keys, and with that, all the binaries.
Okay, so thanks, Derek. You got us all the keys, which is really nice. So now we can analyze the kernel white box instead of black box, which means we can read the code. And the first thing you do when you want to exploit something is you find out the memory map, because you want to corrupt memory eventually. Where should you write? So the kernel is mapped to the high address somewhere, FFFF, BFC. It's read execute. But this is a virtual address that maps to DRAM. And then they have a DRAM mirror that's read-write. So we can actually bypass the read-only portion by using the other address instead. And the 3DS had the same flaw. But I think their thinking here is that, yeah, it makes the code a lot cleaner, so they just always keep this DRAM mirror inside their address space. All the objects are allocated using a slab heap, which is like one heap per object type, and all the allocations are of the same size. So this makes use after freeze really difficult to exploit because you can't overlap two objects of different type, which you usually want to do. So you can only overlap an object with a different object that has the same type. So some of the fields will be different, but most of the pointers are still valid for both objects, will still be at the same offset. So yeah. And now the kernel cannot execute userland code because they use the privileged execute never bit PXN, which is a hurdle that you have to get through. I'm not sure if anyone paid attention. So just to explain, the string to the right is the permissions. So the first three are privileged permissions, and the lower three are userland permissions. And there's something a little bit weird here. So they accidentally mapped the kernel into user space as executable. It's mostly useless, but it means that we can use these. We can just jump into kernel from user space, and it will execute kernel functions in user space context. But we can use this as an ASLR bypass because the kernel is always mapped at the same address, so we can use it for gadgets. But we haven't really owned the kernel yet, so the IOMMU is one of the parts of the kernel you can attack. It's implemented in the memory controller of the SoC. The idea is that all of the non-CPU bus masters are protected, so you assign it an address space identifier ACID, and then you assign a page table to that ACID, and every device that goes through the IOMMU can only access what's mapped in the page table. And the kernel maintains this page table. That's why it's secure, so a malicious driver can't violate the process isolation. And so this enforces that you can only access your own heap through DMA. There's a functionality for accessing another process heap as well. You can lend memory, but yeah. So how do we bypass the SMMU? So we got the official data sheet, the 3,000 pages, and we can just search for bypass the SMMU. I guess it's... So the GMMU is a memory management unit inside the GPU, and yeah, it supports bypassing the SMMU. So NVIDIA backdoored themselves. So this is a GMMU attack. You can set bit 31 in the page table entry, and yeah, it's in hardware, so you can fix it. NVIDIA, thank you. So this is one way of doing it, and they can fix it. But we also had a different way of bypassing the SMMU, and it has to do, it's a trust issue. So the loader loads the permissions that we have from FS, and if we own FS or if we have a vulnerability in FS, we can just tell it what we're allowed to do. So we can tell it we should be allowed to access the memory controller, and then we can just assign acids. So we can assign the acid 0 here to our device. Just means don't do any virtual addressing. So we can DMA all over DRAM, pretty much. So the answer is simple. We can the kernel is in DRAM, so we can just DMA it. But that doesn't work because there's a hardware security feature in the memory controller. You can specify a contiguous memory range that's protected from DMA, and they protect this to include all of the kernels, so we can't really touch it. But we inspected the code a little bit more, and when they allocate the handle table, there are two different ways of allocation. If you have a small handle table, less than 40 capacity, you just use the internal struct as storage. But if you have more than 40, they allocate it in the pool, and this is the same pool that's used for all the memory of all the user processes. And this pool is not protected by the carve-out, but the handle table just is trusted, like it contains kernel pointers and everything. And yeah, we can just DMA it. So we can create a shared memory object, which is just a primitive that the kernel provides. And we can tell it to share the kernel and then we can inject it into our handle table of our process. And then we can use the syscall to map it into our own process. So then it will map the kernel into our process, thinking it's shared memory. And then we can just patch it or insert a backdoor or anything. So this is the way we own the kernel. And here's some code. Yeah. And now we're going to talk. Now we're going to talk a little bit about trust zone. So network.
All right, so trust zone is this nice execution environment by ARM. And we already seen there glitching actually gave us a method to decrypt package 1.1, and it just contains the trust zone payload. And now what I will show you in the next 10 minutes or so is why we can actually ignore this trust zone at all. So the ARMv8 supports trust zone. The code running under secure AL3, which is this trust zone as we call it, is called the secure monitor. This is an official name. Nintendo calls it the same. But on the Nintendo Switch, it doesn't monitor anything, all right? So the secure monitor. It's the first code that runs on the ARMv8, the main CPU. So the ARM7 decrypts package 1.1. It writes the trust zone payload to TZ RAM. That is what we saw. It's this small RAM in the ARMv8. That's this trust zone secure memory. Boots up the ARMv8. Jumps there, and then this is actually the first task of the secure monitor already, is booting the Horizon kernel, all right? So we saw this package 2. At this point, package 2 will be in main RAM. Then the secure monitor will start deriving some keys, decrypt package 2, write the kernel to the DRAM, and decrypt the packaged modules, and then just start executing the kernel. So this is the most important task probably, or one of the most important ones. And the second most important task of the secure monitor is actually cryptography. So cryptography is not directly done in software by the secure monitor, but they actually make use of this nice security engine that is provided by NVIDIA, the Tegra security engine. And some not so important task is trust zone, or the secure monitor, is actually used to stop the additional CPU cores. As we've seen, we have 4 CPU cores. We start executing from core 3 initially, so we have to have means to stop the other cores. And the last important part is the sleep mode. So the Tegra actually supports some deep sleep mode to save some battery. This is always a nice feature of Nintendo consoles. They usually live very long through the sleep mode. Now, if you take a good look at this list, this is actually not important for homebrew at all. That's why I said we can really just ignore the trust zone completely. But let's look at it anyways, for completeness sake. So the Tegra SE, I mentioned it's a hardware crypto engine. It supports AES, SHA, RSA, RNG, all the good things. And maybe you remember from the 3DS, they had this key slot concept. It's apparently a good concept, so they kept it for here as well. So you have 16 key slots for AES, 2 for RSA. You can lock them individually. This is, for example, what the boot ROM uses. The SPK is written to a key slot. It's locked, so you can't just read it out. I mean, it gets cleared once we're in this area, but the trust zone code does the same. It derives some keys into the upper key slots and locks them. So even if you get code execution in a trust zone, you wouldn't be simply able to just read out these keys. So that's quite secure. All right. And what's another interesting thing about the Tegra SE is that the crypto operations actually don't just operate on memory. You can actually encrypt and decrypt between key slots. So this actually enables you to do some secure key derivation. So you could imagine having a key in one key slot could be locked, and then you could actually decrypt this key slot into another one without ever having any keys leaving into memory. So this, maybe you could think of some cool things you could do with that. So how does the cryptography work? So on the left side, you see the secure world. This would be the secure monitor. On the right side is the non-secure world or the user mode. Mostly this is used in the file system module. So what you have to do, at first you have to request a key encryption key. And then the secure world will generate this key encryption key. You pass some parameters. It'll wrap the key encryption key. And this is where the important part comes in. It'll actually use a random session key. So even if you get a key encryption key from one session, once you reboot your console or your switch, the next time it'll be invalid. So even if you, for example, exploit the file system module and grab one key encryption key, you won't be able to use it after the reboot. So this is secure design there. But on the other hand, how do you use these key encryption keys? Well, you pass an encrypted key into secure world along with a key encryption key. Then this is unwrapped, the key is decrypted, and then a plain text final key actually is passed back to user mode. So that's quite interesting. So what you actually find is that, for example, the file system module doesn't use the hardware crypto engine to decrypt games or binaries or whatnot at all. So this is all done by accelerated hardware, accelerated ARM instruction actually. So in theory, you could, for example, exploit the file system module, get some permissions, and then ask the secure monitor to derive all the keys for you. All right. So this is another reason why it's not really important. Now, the last task we've seen is the sleep mode. So this is actually a string from the secure monitor. They call it Oyazumi. Apparently it means good night or something. And so on the SOC, there's this small thingy. It's the power management controller. And this controls the sleep and wake transitions. And on system sleep, the entire system on a chip is powered down, except for the PMC. So there's a small block that's always on. And the DRAM is put into some self-refresh mode so that it keeps the contents, right? Now, if you enter sleep mode, the secure monitor actually has to save some states, right? So what it does, it spills the secure memory into external DRAM, which is untrusted, but it's all right, it's encrypted, so don't worry. And it also authenticates the TCRAM to PMC, so it's encrypted and authenticated, so you can't just mess with it, right? And it tells the security engine to save its context to DRAM. You also have to retain the keys. I mean, you have to use them after you wake up, right? And then we signal the ARM to put everything into this LP0 mode, which is like the slow power mode. And then on wake up, you just roll everything up from back to the fourth. So this is the Ohio. The boot ROM will restore the SE state from DRAM. Then it'll pass ARM code execution to a signed warm boot bin. And this warm boot bin is a bit like a bootloader for DRAM. So instead from a NAND boot, a cold boot, we're doing a warm boot, so from DRAM. And this one would be signed, that's all nice. What this does, it will just decrypt the secure monitor from DRAM to trust on RAM, verify it with the authentication information that we have left in PMC, and then the main CPU will just resume running. So in theory, this all sounds very good, but for completeness sake, we can just remove the trust from trust zone. So as we've already seen from Pluto, there are some trust issues. We can just ask the kernel to map the lower DRAM where all these states are stored. We can map in PMC into user mode, the PMC registers, etc., etc. And we just seen that these are crucial in the wake-up process, right? We've seen that the trust zone memory is decrypted from DRAM into TCRAM and whatnot. So if you poke all these areas in just the right way, you get code execution from user mode, right? So, yeah. But as I said, it's just a fun thing to do. It's not very useful for homebrew anyways. Thank you.
All right, so it's pretty green. Okay, so what we've done so far is when we pwned the kernel, we made a USB debugger. And it works. You can debug user programs, you can put breakpoints and inspect the registers. You don't get the symbols yet, but it's open source, so if anyone wants to add it. It currently requires a kernel exploit, but we don't share it, but hopefully someone will make their own after this talk. But yeah, what we really care about is homebrew. So we've made libnx, which is a user mode homebrew library. We provide all the kernel primitives, like you can create threads, you can mutex, you can talk to other processes using IPC. We have nice wrappers for everything. We have fully working network, file system. We can act as a USB host. We have the controller's input working. And, let's see here. Okay, so we have frame buffer working, and this took a really long time. I think our friend Yellows8 worked on this for like 2 weeks full time. They're running like Android binder IPC interface inside their own IPC interface. It's pretty crazy, but yeah, we have it working. And we're pushing the updates, so anyone can just use this now. But still there's work to be done, right? We enjoy reversing proprietary code a lot. It's a lot of fun. Homebrew is fun, I hope you agree. And but we still have work to be done, right? So we don't have any GPU acceleration right now in libnx. So right now everything is software rendering. And audio support we don't have right now. So and then we want people to make games, because otherwise the hacking is for nothing. So we couldn't release it today, but we're working on a homebrew launcher. So there will be homebrew soon. It's in collaboration with another team Reswitch, which actually implemented a lot of the exploit. So we're just like trying to make it a nice stable platform for homebrew. And yeah, get on firmware 3 if you're lower, and stay there. So thank you to everyone involved, and especially Yellows8 who couldn't make it. So yeah, we have the demo working, and I'll have it now. Yeah, can we switch? Oh, sorry. So also thanks to is it on? Oh, thanks to Nintendo as well. It's a pretty nice system. What are you doing? Oh, yeah, right.
Like this?
Yeah, yeah,
No.
right. It's the right one. It's the right one. It's the right one. Yeah. Okay. So this is just something I wrote like last night, but hopefully it works. Yeah. Thank you. if we have time for questions, we can have them.
We have time for some questions. There are microphones stationed around the auditorium, numbered 1 through 6. If you have a question burning that you would like to ask, then please, I would ask you to line up behind these microphones and I will call you. Also, there is a signal angel who is taking questions from the internet, and I see that he already has one. So, dearest signal angel, please, our first question.
Thank you. When glitching to get the keys, how long did it take to get the keys with the, the exact right timing? Have you been able to anyhow automate this task?
Sorry, could you repeat the question? The speaker is a bit lousy.
When glitching to get the keys, how long did it take? And could you anyhow automate this task?
Okay, so the question was how long it took to get the keys and if we could automate it.
Yeah, it took about like 1 month to get some key blob keys, and just recently, like I think last week, we got some other keys as well. So yeah. Regarding the glitching setup, yes, it was possible to automate it because we found the reset signal. So after each glitching attempt that failed, we could just reset and try again.
Microphone number 6.
Yeah, thank you for a great talk. I would really like to rebuild your glitch attack. Is this stuff somewhere available?
So could you repeat? It was something about the glitch attack reproducing it?
Yes, I would really like to try it myself. Is this information about the glitch attack somewhere available?
So the question is if the more information is available on the glitch attack. And yeah.
Yeah, well, basically it's just power glitching. There's a lot of information about it, but it's not that difficult. I mean, you saw it was a pretty cheap setup. You just need some MOSFETs that somehow pull the voltage down to ground, and it will just work, I guess.
Microphone 1.
Since there have been jokes about the Switch just being an Android tablet, have you guys tried to start running Android or Linux on it yet?
No, we didn't try that yet, but I think it would be pretty sweet to have Android running on Switch, yeah. But yeah, I think it would only make sense with some kind of cold boot exploit, and yeah, we are still working on that, so yeah.
Signal angel.
Thank you. So you told about doing crypto on the key slots. Could you copy an encrypted key from a locked key slot into an unlocked key slot, read it out, and then decrypt it?
So there are bits that actually, or the question was whether you could copy an encrypted, a locked key slot into an unlocked key slot and then read it out. So there are some bits that actually controls whether you can write from a locked key slot, and you could actually set it up such that you wouldn't be able to encrypt from a locked key slot into an unlocked key slot. So you can actually make it secure. This is one attack that we've thought of, but there are mitigations against this attack by the locking mechanism. So unfortunately that's not possible if you set it up correctly. Thank you.
Microphone 4.
Yeah, thank you very much. You just told us that we should stay on exactly firmware 3.0.0. So what did change from 2 to 3 that doesn't make homebrew feasible on that version? And what was patched for 3.0.1 so that it doesn't work anymore?
Yeah, so the question is why Homebrew won't work beyond 3.00, if I got it right. And the reason is that the bug we talked about where you don't send the PID, so it thinks it's PID 0, they fixed that bug on 3.01. So if you're below that, you're still vulnerable, but if you're above that, you can't bypass the whitelist and you can't really get anywhere. Yeah, so that's the answer to that. But something I was going to say. Yeah, I'll probably Yeah, it wasn't anything important, probably.
Microphone 2.
Yeah, so this exploit works on Puyo Tetris, but have you been able to test it on other WebKits like the captive portal?
Yeah, so the question was if the WebKit exploit only works for this Tetris game. And no, the answer is that the WebKit is not actually bundled with the game. It's more like a system applet. So the game just launches an applet from the system firmware. And so we have the same bug, the Pegasus one that we demoed. It works up to 2.3, I think. And then they fixed it, and then it will be fixed for all of the games. But yeah, if you're on above 2.0, you don't really have to buy this game, this Tetris game. You can just launch it without it. So.
All right, that was all the time we had for questions. Let's give them another round of applause.